Okay, so shall I start, sir? So, good morning, friends. Uh, in the today's session of COA, we will have some questions of for the remaining part that we left yesterday. Okay, so yesterday we just covered some of the important topics that are pipelining, addressing modes, instruction format, very important, and the control unit questions. Okay, and some of the sample questions that relate most of the topics with the COA subject. Okay, today we are going to cover the remaining of the topics that we left yesterday, starting from the topic name cache and memory organization. Very important topic. You will find so many questions in the previous year books. Okay, then secondary storage and IO structure. Okay, then data representation. This data representation is basically the part of digital electronics. But as it relate with COA and relate with COA very much. That is why I'm covering some of the questions here. Okay, so you will find some data representation questions as well. But it's majorly according to the IIT syllabus. It is the part of digital. It is the part of digital electronics. Okay, but I'll cover some of the questions so that you may have some teaser or friendliness about the questions. Okay, these are the major topics that we are going to cover today. Okay, in which the cache memory and the memory organization is most important among all those. Okay, IO and secondary storage also mild important, but data representation you will find most of the questions in digital electronics and so many questions about the fixed point and floating point representation, especially the floating point representation, that is IEEE format of 754 FPR. Okay, so you will find a number of questions about that. uh, so if you guys are available or online, just let me know or acknowledge. And if you have any doubt regarding the last question we had yesterday, okay, about this Indianness, if you are unable to understand that, let me cover that question first. Let me clear that doubt first, because it's a very important topic. Why you need the Indianness and why we need the mechanism behind this is a highly conceptual thing. If you finding any trouble with that particular question, the source code of the programming or pointer question, just let me know. Do I have to recall or re explain it or not? As a start, just say good morning. Just start with the greetings. Omkar, very good morning. About the last question, I'm repeating it again. About the last question we had yesterday of Indianness and the architecture, how you come to know that the particular code or piece of code will tell you about the architecture behind your system or computer. Very good morning, Muskan. If you have any problem with that question, just let me know. Otherwise, we should start with the fresh one. Very good morning, Pritama. Hi, good morning, Bhavya. Do I need to explain it again or should I start with the fresh one? Just let me know. Okay. So let's start with the first question today. Express 15, which is in decimal, in IEEE 754 FPR hexadecimal format. Okay. And we have four options about it. So IEEE 754 is the standard IEEE format, which is used to represent the floating point number. Okay. So, but we need the 754 FPR hexadecimal form. As you see, the options are given in the hexadecimal format. So we need to convert 15, which is in decimal, into the hexadecimal format 754 FPR based on IEEE standards. Okay. This particular topic is from fixed point or floating point representation, which is data representation. Okay. So I'm taking this simple topic as a start so that you may have the understanding of the question. This actually comes in the part of digital electronics, but I'm covering it here. Okay. So how do you actually convert this 15 into floating point representation? Let's go with this, that the format of floating point, or for floating point, the floating point format are actually of two types. First, single precision. First is single precision, and the another one is double precision. Okay. Single precision is basically has a size of 32 bits, and double precision is of course 64 bits long. Just take it that way, that to store any variable in C or programming in C, we have two floating point data types, not the modifiers but the data types. One is float, another is double. Float is usually of 4 bytes and double is of 8 bytes. Okay. So here single precision is just like the float data type in C, and the double precision is just like the double data type in C. Okay. So based on these, the floating point values or variables get stored in the programming. Okay. So wherever, whatever you do with the programming part, it should supported by some architecture, because based on the architecture the things are going on. Okay. So physically they need to get stored, or logically they need to get stored, but only in the basis of, yeah, only the basis of organization and architecture. If organization and architecture allows it, you may use the following properties or facilities or features. Correct. So as you see the options, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 hexadecimal values. So 8 hexadecimal values, that means the 32 bits representation is there. Okay. As compared to double precision, this value is less. Okay. Half of the size. So the single precision format of IEEE 754, we should know about that. And based on that, we are going to convert 15 as IEEE 754 FPR hexadecimal form. Okay. So IEEE single precision, IEEE single precision format, which is 32 bits, is look like this. Okay. We don't need double precision here. We only need the single precision one. So this is the format the IEEE 754 FPR format looks like, or the single precision format of floating point looks like. So we need to find the values of S, M, and the BE. Here, S is the sign, M represents mantissa, the fractional part of the floating point value, and BE is denoted by biased exponent. And here 127 value you are looking at is basically called the bias. Fine. So we need to find these three values so that we can have the particular format and then the calculation of the 15 in hexadecimal form. Okay. So just let me put this apart. Okay. So let's start with 15 in the decimal. How you convert this into the floating point value. So 15 in decimal should break in at as like 2 to the power 3 plus 2 to the power 3 multiplied by 1.875. All we need to do is we need to find this type of value, the fractional value out of the decimal value. Okay, and we need to find the another value which is based on the power of 2. So if you see, 15 lies between 2 to the power 3 and 2 to the power 4, which is among 8 and 16. The 15 value lies between 8 and 16 based on the base 2. Okay, so all we need to break is just check it out where the 15 or any decimal value lies in case of, or in the basis of, with respect to the power of two values. So 2 to the power of 3 is basically 8, so 15 is bigger than that, and 2 to the power 4, which is 16, is actually greater than 15. So 15 lies in these two values. Okay, so if we take out 2 to the power 3 out of 15, the remaining will be the fractional part, which is 1.875. You can calculate it. Okay, so out of 15, if we pull out the value 8, which is 2 to the power 3, because we cannot pull out 2 to the power 4, which is bigger than 15. Okay, so the closest value we can pull it out is 8. So out of 8, 15, the remaining fractional part will be 1.875. This 1.875, we can write it in Mantissa form or in the binary form. We can find it as, we can convert it into the binary form. Okay, and this 2 to the power 3 comes in this portion. Okay, we can use this power to represent in this format: 2 to the power biased exponent minus 127. So all you need is to break this value in two things. One, the 2 to the power, and the another, the remaining fractional part after dividing the value. Okay, so 15 can be written it as 2 to the power 3, which is 8 into 1.875. Okay, out of which, if you can see, this 2 to the power 3 is basically positive value, or 15 is basically the positive value. So out of this plus sign is going to be the sign value, which is representing whether the value is positive or negative. Okay, this 2 to the power 3 is going for the calculation of biased exponent, and the remaining part 1.875, out of this, the 875 is going to be the mantissa. Okay, now how do you calculate the biased exponent based on this? So here, let me write it down. The biased exponent is basically equals to actual exponent minus bias, sorry, plus bias. Or let me write it down the full version. biased exponent is equals to actual exponent plus bias. We already know what is the bias is actually 127 according to the IEEE 754 uh, single precision FPR. Okay, so bias is already 124 and the actual exponent we just calculated it as 3. Okay, so the biased exponent BE should be 3 plus 127, which is 1, 3 and 0. This will be our biased exponent. Okay, so this is how you calculate three values about sine, the biased exponent, and the mantissa, and you can put it in the given IEEE format. Okay, now the only thing you need is the binary format of 875 as a fractional part. You need to find this fractional part in the binary. So how do you actually find it? So to find the binary of the fractional part, how this is going to be? So the first value should be half, another value should be 1 by 4, then 1 by 8, then 1 by 16, then 1 by 32, and so on. Okay, and then you can add these values to find the same value which you are using to convert. So 875 should be the total of zero point 0.5 plus 1 by 4, which is 0.25, plus 1 by 8, which is going to be 0.125. Okay, after calculating this, you are having the same value 0.875. One is already there. One is already there, but the 0.875 can convert it into zero point 0.5 plus 0.25 plus 0.125. So all you need is to subtract this value from 0.875. Whatever is the remaining, trying to subtract it with another value, and you will find the binary. So if this and this value is going to subtract with this and the value will remain 0, this means the binary of 0.875 will be 1, 1 and 1. Okay, the rest of the items are 0 now. So this is going to be the mantissa. This is going to be the mantissa. Okay, this is going to be the mantissa. So if we write this all the values into the format given, so this will become like minus 1 the sine, multiply by 1 into m the mantissa, multiply by 2 to the power biased exponent, which is 130 minus 127. Now we already have mantissa, so let's put it in here. So this will be like 1.111 multiplied by 2 to the power 130 minus 127, and the sign is, again we have already calculated it, because the value is positive, sign is actually 1, sorry, sign is actually 0, which is representing the positive value. Fine. So all you need is to calculate these values. Fine. And it to calculate these values in the hexadecimal format, there is another format about single precision. Just let me have this format. So this format must be 32 bits long. Okay. One value or one bit is reserved for the sign bit. Okay. Another, for biased exponent, another 8 bit is going to reserve. Okay. So let me have this clear, that this is 1 bit, This is 8 bit and the remaining 23 bits is for Mantissa. Okay, but this one bit represents the sign, this represents the biased exponent, and the remaining Mantissa will be here. So sign in our case is 0. Okay, the biased exponent is basically 130. So 130 in binary, we can write it down it as 128 plus 2. So 1, 2, 4, 8, 16, 32, 64, and 128. So this will be 1, 2, 3, 4, 5, 6, 7, 8 bit representation of the 130, which is the biased exponent. And the remaining Mantissa, the M part will be 1, 1, 1, and the remaining 20 bits will be 0. Okay, so this will be the full 32-bit representation of decimal value 15, and you can easily convert this into the hexadecimal. How to convert this into the hexadecimal? Let's find it out. So first four values, then another four bits, then another 4 bit, another 4 bit, and so on. This is how you find out. So if you see it closely, let me zoom it for you. This first 4 bit, okay, this first 4 bit is the binary of that is 0100 is the binary of hexadecimal value 4. The another 4 bit, which is 0001, is the binary of 1. Another 0111 is the binary of value 7, and the rest of 8 or 5 values will be 0. So the remaining part will become 0, and this representation is in hexadecimal format. So the 15, which is a decimal value, is going to be converted into IEEE 754 FPR hexadecimal format as 417 and 5 times 0. Okay, so according to this, if we have the right option over here, the correct answer is option B. Okay, the correct answer is option B. 417 and 5 zeros in hexadecimal format. So again, I'm explaining it, or I'm briefing it. uh, just to break the decimal part into two things. First, the power of 2, and the remaining part will become, or will go for the Mantissa calculation. Third thing you need is to find the sign. If the sign is positive, the sign is 0. If the value is negative, the sign is 1. Okay, then put these three values, okay, in the given 32-bit of format, which is -1 to the power sign into 1 point Mantissa into 2 to the power biased exponent minus 127. Okay, just put these three values and convert this Mantissa fractional part into the binary, just like I told you. Okay, after putting this, put these three values in the 32-bit special format, which is designed for single precision. Okay, where sign take 1 bit, biased exponent take 8 bits, and the remaining 23 bits for Mantissa. Once you design the format in the binary, you can convert easily it into the hexadecimal format. Okay, so these type of questions usually come in the GATE examination. You must have the knowledge about this. These are simple questions, but you need to remember the format at least. Okay, so let me have then some space over here. Okay, if you're done with the first question, let's go with the second question. The second question is based on, this should be some typing mistake. uh, it is actually 16-way set associative cache. Okay, let me zoom it for you. Fine. So, about the second question, a 16-way set associative cache has 16 bytes of block size and 32 byte addressable memory. So it is already given the addressing format. The addressing format is basically the byte addressable memory. The total bits required for both tag, word, offset for any CPU reference is, we need to find out if the cache is of size 16,384 bytes. Okay, so you need the total bits of tag and word offset. So all you need to first understand this, that what is the set associative cache and how the set associative cache format looks like. Okay, so I'm writing it over here. The set associative cache format looks like this. This format has three things. First, the tag bit, another is the set, and the last one as the word offset. This is the format of set associative cache. This is the format of set associative cache. So all we need to find that number of bits in the tag and word, and then we need to total them. Okay, but how we are going to do this? So first thing first is, what is actually set associative cache? So set associative cache is basically the overcome of a direct cache or direct mapped cache. So direct mapped cache is basically a single dimensional array or 1D array, or you can say it as a 2D array, but you can only store one block of memory at a time. So direct memory should look like this. If you have the knowledge of data structure and hashing, this is generally exactly the same thing. It actually do the same thing just like the hashing does. Okay, in the hashing also we always have some bucket numbers or the bins, and to put some key or data into this bins, we need some hash function behind that. Exactly the same thing goes with the direct mapped cache. In the direct mapped cache also, we should have some mapping function in which the k represents the data or the memory reference, and m represents the size or the number of blocks in the direct mapped cache. Based on this particular mapping function, you put any data or key inside the direct mapped cache. But the only issue is, suppose if this is 0, 1, 2, and 3, and if the key is 10, okay, so that should be 10 mod the number of blocks or number of block space is actually the 4. So if you go with this, the mod will become 2. So this particular data or reference 10 goes into. Now the another value comes as let's suppose 6. Then 6 mod 4 again becomes 2. So this is going to be the collision when number of data or multiple data is trying to occupy or accommodate into the same memory block, same cache block, then it is going to be the collision just like hashing does. So in that case, the new block, which is the 6, is going to overwrite 10. The only issue with the direct map is this: only one block you can put at a time. Okay, that is why we use the set associative cache, so that you can have multiple blocks inside particular set. So we are going to have sets where you can put a number of blocks simultaneously, but once the blocks are going to be full, you are going to replace it by using some replacement algorithms that are least recently used or the FIFO. Okay, but that is a different thing. All we need to understand, what are the set associative cache, what is the set associative cache is. So Let me get back to with this question. Okay. So about this question, what data is actually given here is 16-way set associative cache. 16 byte is the block size. 32-bit is byte addressable memory. Hence, the memory or the format is actually 32-bit. So let's write it down in here. This particular format is actually 32 bits long. Okay. And the total you need to find between tag and word. So all you need to find is the full format of this. The size of the cache is this. Okay. So first you need to find the number of cache lines. What are the number of cache lines? Number of cache lines you can find with the help of cache memory size divided by the block size. In our case, which is 16384, which is in bytes. Okay. And the block size is already given 16 bytes. So bytes got cancelled. Remaining is 16384 divided by 16. Now, to solve this, just convert this into the power of 2. So if you do the power thing, 16384 is basically 2 to the power 14, and 16 is 2 to the power 4, which is actually equals to, if you erect this, which is actually equals to 2 to the power 10, which is 1024. Okay. So number of cache line is we have here is 1k, around 1k. Okay. This number of cache line is actually the representation of direct mapped cache, but we actually divide that direct mapped cache into the set associative cache. So in set associative cache, all we need is to find the number of sets, but not the number of cache lines. Number of sets will be the number of cache lines divided by the p way. Now, what is this p way? Let me have the direct mapped cache example once again. So here you are going to have 4 cache lines. These are the cache lines. Okay. But the only issue is in direct mapped cache, you can only accommodate one main memory block into the direct mapped cache. So for simultaneous storage or multiple storage, we divide this direct mapped cache into the number of sets. So let's suppose we have two-way set associative cache in here. So all you need to do is the number of cache lines, divided by this p way. This is what we called p way. So so this p way is actually 2 in our case in the given example. Okay. Number of cache lines we have 4 divided by 2 is basically 2, or 2 to the power 1, you can say. So the number of sets we are going to have 2. So the set associative cache in our example given is like this, should look like this. Fine. And among those, we will have two-way set associative cache, which should look like this: 0, 1, 0, 1, 0, 1, 0, and 1. So the size of the cache memory will remain same, but the representation or structure gone different. In direct mapped cache, you only have one main memory block accommodated, but in here, in one set, you can have two main memory blocks at the same time. But once the set is full, you need to replace this block with some another fresh block. For that, you need uh, memory reference representation or replacement algorithms. Okay. Replacement algorithms are going to work here then. Okay. Very good, Sneha and Omkar. The answer is 26. Fine. So this is how the set associative cache looks like. So all you need is the number of cache lines divided by the p way. So number of cache lines, we have already calculated it as 2 to the power 10, and the p is basically given as 16, which is 2 to the power 4. This is going to be 2 to the power 6 sets. Okay, so if 2 to the power 6 sets, the log of this will give you 6-bit representation for sets. Okay, just like we did it yesterday, that 32 instructions are there. So 2 to the power 5 is the number of bit representation in the opcode. Similarly, if 2 to the power 6 sets are here, 6 is the number of bit representation for set. Word, what is the word based on the block size, and we already have the block size, which is 16 bytes. So 16 byte is basically 2 to the power 4. Hence, 4-bit representation is required for the word offset. And the remaining out of 32 will going to be in the tag bits. So 32 minus 10, 22 bits are going to required for representing the tag bits. Okay. Once you design this particular format, all you need is to find the total number of bits, which should be the tag plus word. The question is asking about tag and word number of bits in total. So this will be 22 plus 4 is actually equals to 26 bits are going to require. Okay. The total of tag and word offset number of bits is 26. This should be the answer. So this is how the set associative cache get converted from the diet memory cache. So the structure will be different, but the size of the cache will remain same. In here, you are having only 4 memory blocks at the time. If you have different memory blocks on different spaces, and in here also you are having 4 spaces for memory blocks. So the number of memory blocks will be same, the cache memory size will be same, but the structure and representation will be different. Okay, so these are the important formulas you need to remember. Fine. If this is clear now, let's move on to the next question. Let me have some space over here. Okay, we are having another set associative cache question. Okay, but based on this is actually based on the replacement algorithm. So in here we are using FIFO scheme. So let's consider two-way set associative cache consisting of 4 blocks. Okay, these 4 blocks is the block size. This 4 block is the block size. For choosing the block to be replaced, use the FIFO scheme. This is important. FIFO is actually work just like in the queue. Okay, the number of cache misses we need to find, the number of cache misses for the sequence of block addresses, and the addresses are given here. So what are these cache misses actually? So the architecture behind this actually works like this. So CPU, which actually wants the data to be processed, is not connected with the main memory or the secondary memory directly. It is actually connected with some intermediate memory in between, which is what we called as cache memory. Okay, and in some processors or some systems we can have multiple cache memories in between, but that is a different thing, different topic. Let's not go there. So CPU is actually connected with some intermediate memory between main memory. So there must be some intermediate memory, which is the cache between CPU and main memory, and then main memory gets connected with the secondary storage or secondary memory, which is the hard disk. This is how the organization actually looks like. So CPU can't do the read and write operations here. Okay, CPU only knows about the cache memory. It can only read and write on the cache memory only. Okay, So whenever CPU is requiring any data, it is not possible to have all the data in the cache memory. So that data particularly is going to be miss in the cache memory. Then once it miss in the cache memory, the reference is basically transferred to the next intermediate memory connected. Then the next intermediate or system supported memory is the main memory or RAM. If the operation is hit, or if you find the data in the main memory, that is fine, and then the data is again transferred back to the cache memory and then to the CPU. But if there is a miss in the main memory, hence the memory doesn't contain that particular data or block, this reference is again transferred to the secondary memory, and you are able to find every data in the secondary memory. So basically there are two factors here, which are number of misses or miss ratio or hit ratio. If there is a miss, it is going to be a miss ratio, or if it is going to be a hit, there will be some hit ratio. So hit ratio for secondary memory is always considered as 1. So whatever CPU is looking for is going to be hit in secondary memory. So secondary memory has everything, but cache memory and main memory are not that much of size. So because of small size, especially cache memory, there are number of misses to be find out. Okay, but because the structure or the manufacturing says the cache memory is quite faster than the main memory, and main memory is faster than the secondary memory, we use the cache memory as intermediate memory between the memories, or CPU and main memory. Okay, fine. So frequently read data will be in the cache memory, but not always you can have the hit. So the number of misses in the cache you need to find out here. This organization is what we call is memory hierarchy design. This memory hierarchy design actually used to make the system fast, and it actually used to design or to show the number of system supported memories at a time by the system, and there are so many factors behind this also. So this particular on based on this particular hierarchical design, okay, the cache memory misses we need to find out. So first we need to construct the cache memory, which is set associative cache, and then we are going to have some misses and hits. Okay, so to design the cache memory, all we need to find is the number of cache lines first. But this is already given directly that the cache memory consists of 4 blocks. So 4 cache lines are there. But to design the set associative cache, we need the number of sets, which are the number of cache lines divided by the p way. Number of cache lines are 4 and the p way is 2. Hence, the number of sets we have here is 2. So 2 sets will be here, and each set are going to have 2 ways. So the set associative cache will look like so 2 sets will be 0 and 1, and then we can have the word offset as this. So 2 sets and both set are having 2 way in behind. Okay, in the inside. So to get the values or to get the data into this particular cache, you must have some mapping function also, just like in the direct mapped cache. So because you have this number of sets as 2, the mapping function will be k mod m, where k is the memory reference and m here represents the number of sets. Same in the direct mapped cache, K represents the memory reference, but M represents the number of cache lines, because we don't have sets in the direct mapped cache. So all we need to find is the mod from the number of sets, and we can accommodate the reference or memory reference in the given sets or calculated sets. And once the sets are full, Okay, you are going to replace it from the new block or new memory reference, and for that you have the algorithm or scheme here as FIFO. Okay, so let me zoom in for you guys so that we can have the clear view. So starting from 18, first reference. So when the CPU is looking for 18 in the cache memory, initially the cache memory must be empty. Hence, it is certainly the miss. So for the first reference, which is always also called the compulsory miss, when the reference is going to be in the cache for the first time, it is already not available in the cache memory. Hence, the CPU will find this as a miss. The operation is going to be a miss, and then the reference is then transferred to the main memory, just like here. Then the reference is transferred to the main memory, and it's main memory responsibility to give it back to the cache memory so that the CPU can have the data. Okay, so CPU is asking for 18, which is not present in the cache memory, and the reference is transferred to the main memory. Okay, and main memory will transfer it back to the cache memory, so that CPU can read that particular data. But still, it is a miss operation in the cache memory at the first time. So 18, if comes back from the main memory, then 18 should be accommodated in which set, that you need to find out by using the mapping function. So in our case, k mod 2. So 18 mod 2 becomes 0, which means 18 goes to the set number 0. But it is already a miss operation. Next time, the next reference is CPU is asking for the next reference of 12, but 12 is again not present in this set or set associative cache. Hence, it is again going to be a miss. Fine. And back from the main memory where you actually accommodate 12, that is going to be calculated as 12 mod 2, which is again 0. So as you see, every value here is an even number. So every time we must be using the set number 0. So every time when the set is full, the new fresh block is going to override the previous block in the cache memory. And for that, you need the FIFO scheme. So now the mod will always give you the set number 0. So let's not doing it again and again, and doing it fast, we can have this 12 value in the next block. We cannot overwrite this into the 18 because we already have the space in here. So 12 will be in the vacant space first. Once the set is full, the next memory block is going to override the current items in the cache memory. Okay. Next time, CPU will ask for 100, but 100 is again not present in this set associative cache, hence it is a miss. But 100, when comes here, find the set is actually full. So 100 is going to replace some existing memory block, and which is going to get overwritten. Whoever comes first. So first in goes first out. So among 18 and 12, 18 comes in the first place. Okay, so 18 is going to be overwritten by 100, but as 100 is already a miss. Next time when CPU asks for 12, 12 is already present in the cache memory, so this time CPU got it as hit. Okay, next time 18, 18 is not present in here, hence it is certainly a miss operation, but 18 is going to override some of the items here. So among 112, okay, 12 comes first, or the timestamp of 12 is the longer one, so 18 is going to overwrite 12. Fine. Next time, memory reference 12 is not actually present in here, so operation is certainly a miss operation. And among 100 and 18, 100 has the most 100 has the most longer timestamp. So 100 is going to get replaced by 12, or 100 comes early as compared to 18. Next time we just override 100 and there's a reference of 100. So certainly it's again a miss operation. But among 12 and 18, 18 has a longer timestamp. So 18 got overrated by 100. Next time, the memory reference 18 is going to be a miss operation. But among 12 and 100, 18 is going to replace 12. Again, next time, the memory reference 12 is going to override 100. Sorry. Okay. But as it is not in the cache memory block, so this is a miss operation. Now, the last but not the least, 18. 18 is already present in here. Hence, it is certainly a hit operation. So all you need to calculate is the number of misses we can have. So this is 1, 2, 3, 4, 5, 6, 7, and 8. So 8 cache misses are there. 8 cache misses are there. Okay. This is the right answer. Fine. This is how you do these type of questions. So you need to calculate the number of sets, then you must have the mapping function, and to replace the existing items you must have some following scheme, either FIFO or the least recently used. Fine. This memory hierarchy design comes in one more fashion, that is memory simultaneous design, and that should look like this, where CPU can simultaneously connect it with the number of system supported memories. So this organization is much faster than the memory hierarchy design, because when CPU is going to have some data in the cache memory, and once the operation is going to be missed, the reference is transferred to the main memory. But when main memory find that data, it can directly transfer it back to the CPU. There is no need to transfer it to this cache memory and then to the CPU. So the time access, sorry, you can say it as access time for the CPU to access that particular data from the main memory is very less as compared to here in the hierarchical design. In hierarchical design, the data first transferred to the cache memory and then to the CPU. So the access time becomes large. Okay, but in the simultaneous behavior, access time is much smaller as compared to hierarchy. So this is much efficient design, but very much costly. So these type of organizations we use in supercomputers or some other machines. Okay, so this is what we call simultaneous. Okay, fine. Let's move on to the new question. Let me have this here, and let me shift these. Okay, fine. So the next question is from secondary storage. Okay, consider a disk pack with the given specifications. So here we have 8 platters, 8 platters, 128 tracks, 512 sectors per track, and 256 bytes per sector. So to have this understanding, I'm using a disk view. the top view of the disk so that you can able to understand what is going on here. So this is actually one surface, and these are the tracks over here, and these tracks are divided into the number of sectors. So these are the sectors. Okay, and we have some certain size of sectors that is already given in our given our question, 256 bytes per sector. So one surface consists of multiple tracks. One track can have multiple sectors, and each sector has some certain specific size. Fine. What is given in the question then? Consider each surface has only one read write head. One read write head is given because in one revolution, whenever you have the revolution of the disk, in one revolution you always going to read one track. That will help you to find out the data transfer rate. That is what the question is asking. What is the data transfer rate in mbps, megabytes per second, if the disk is rotating at 7200 rpm? Okay, so all you need to find is the data transfer rate, and to find the data transfer rate you must have the revolutions. Okay, and the total data on the single surface, or what in one revolution how much data is going to get transferred, that is the number of data in particular track. So let's have the formula of data transfer rate. How you find the data transfer rate is basically this. So the data transfer rate is actually equals to the number of surfaces multiplied by the total time taken on one surface divided by time taken to transfer that data. I'm going to explain it for you. Okay, so the data transfer rate is the number of surfaces and the number of surfaces multiplied by the total time taken on one surface, or sorry, the total time taken, let me correct this thing, this is not correct thing. The total time taken is not the correct thing. Total data should be there. Total data on one surface divided by total time taken to transfer that particular data on the surface. Okay, correct this one as total data on one surface. Okay, now first you need to find the total data on one surface. So total data on one surface is, so one surface can have number of tracks, and then number of sectors per track, and then number of bytes per sector. Okay, so number of tracks multiply by number of sectors per track multiply by number of bytes per sector. This will give you the size or total data on surface 1 or one surface. So this is already given in our question. So number of tracks we have 128. Multiply by number of sectors per track are 512, and the sector size is 256 bytes. Okay, let's convert them into the power of 2. So this will be 2 to the power 7 into 2 to the power 9 into 2 to the power 8. So this is going to be 7 plus 9, 16 plus 8 is 24. So 2 to the 24, 2 to the power 24 bytes we are having per surface. And how many surfaces we are having? 8 platters is given. So 8 platter, each platter has two surfaces, upside and downside. So 8 platters are going to have 16 surfaces. Okay, that is a different thing. We must not require that information here. Okay, so each surface can have 2 to the power 24 bytes of data. Okay, now let's come to the time taken to transfer that data. And to transfer that data in one revolution, you must have transferred one track. Each revolution, you are going to transfer one track. Okay, so for that, you need to find out the disk rotation speed. So how much time one revolution actually take. So already given the data, sorry, the disk is rotating at 7200 rpm, which means one revolution can be done in 60 upon 7200 seconds. How do you find this? Let me explain it in here. Okay, so 7200 revolutions we can have in 1 minute. Okay, which is actually 60 seconds. So if 7200 revolutions are going in 1 minute, how much time will take to revolve one cycle? Okay, that will be 60 upon 7200 seconds. So one revolution will take 60 upon 7200 seconds. Okay, and in one revolution, I already explained, you can transfer or you can have one track of data. Okay, so one revolution is going to be in 60 upon 7200 seconds. Next thing is, if one revolution is there, so in one revolution the read write head can have the data from one track. So let me put in this way, that in one revolution a read write head can read the data from one track. Therefore, the time taken to read one surface will be the number of tracks multiply the time taken by the time taken to read the data from one track. So that should be 60 upon 7200 seconds. Right. So 60 upon 7200 seconds is one revolution, which is equals to the time taken to read the data from one track, and we are already having 128 tracks per surface. So one surface time taken will be the number of tracks into the time taken to read one track. Okay, so here 28, 128 is actually the number of tracks per surface. Okay, and 60 upon 7200 is the time taken for one revolution, which is already I already explained. A read write head can read the data from track one or one track. So once we have this in here, we can put these values in the above equation, the first equation. So the first equation was or will look like this. So the data transfer rate is actually equals to the number of surfaces. So we have 8 platters, hence there are 16 surfaces. multiply by the total data on surface. The total data on surface we are having is 2 to the power 24 bytes per surface. Okay, divided by the total time taken to transfer data. Okay, so total time taken to transfer that data which is on one surface is actually 128 multiplied by 60 divided by 7200 in seconds. So let me put this like 16 into 2 to the power 24 bytes into 7200, okay, divided by 128 into 60. Okay, okay, and we can do one thing also. Let's erase that byte here, and we can have this in bps, bytes per second. Now we need to find the data in megabytes per second, so we can calculate mega from in here. So let's cut this thing into the megabytes. So we can in megabytes we can have 2 to the power 20. So remove this 2 to the power 20, and the 2 to the power 4 is the remaining 4, and we can have the unit in mbps. So this should be 16 into 2 to the power 4 multiplied by 7200 divided by 2 to the power 7 we can use, okay, into 60 in mbps. Okay, so the answer, if you calculate this equation or this expression, the answer will be 240 mbps. This should be the answer. So the data transfer rate to transfer one surface which has 128 tracks, eh, and the rotation speed is actually 7200 rpm, the transfer rate of data is 240 megabytes per second. This is your answer. Okay, so this is very important formula. Okay, no Rishi, this session is not for the EC guys. Okay, in CE or your subject, you don't have these topics. These topics are dedicatedly in the CS branch syllabus, not for the EC branch. Fine. So remember the data transfer rate formula and the way to find all the figures. Fine. Let's have a clear view of this, and then we can move on to the next question. Okay. Again, we are having the same cash question here, but now it's asked something different. A 16-way set associative cache holds 64K bytes of data. Data words are 64 bits each. Remember this thing, data words are 64 bits each. A word addressable memory. Now there is word addressable memory, not the byte addressable. Word addressable memory addresses in 40 bits. Okay, so the format length is actually given as 40 bits. There are 16 words per cache block. This is the block size. Then what is the tag memory size? Okay, so first let's have the format of set associative cache in here. Set associative cache format has three things, three fields. One is tag field, another is set field, and the third one is word offset. and the length of this format is already given as 40 bits. Fine. So there are 16-way set associative cache. There is 16-way set associative cache, 64K bytes, 64 bits of the word size. Hence, the word size is 8 bytes. The word addressable memory has 40 bits. We already taken this. There are 16 words per cache block. Okay. So how do you find the number of cache lines? So let's have the number of cache lines. Okay, so the number of cache lines will be the total size of the memory. The total size of the memory is how many bytes? 64K. 64 KB bytes. Okay, divided by the block size. But block size here is given in 16 words. So 16 words. But we need to calculate these words in the number of bytes because the size is given in the bytes. So let's have this like this. Uh, we can write 64K as 2 to the power 16. So 64 can be written as 2 to the power 6 and K kilo can be written as 2 to the power 10, which is 2 to the power 16 bytes. Okay, multiply by one word, which is actually 8 bytes because one word is already given as 64 bits. So 64 bits is actually 8 bytes. So we can write it as 2 to the power 3 bytes. Fine. Multiply by multiply by one block, where a block size is actually 16 words. So that is 16 words. Hence, we can write it as 2 to the power 4 words. Okay, so we were having 64K bytes divided by 16 words. 16 words means 2 to the power 4 words, and each word is actually 2 to the power 3 bytes, which is 8-byte memory. Okay, so this is how we can write it in here. And let's calculate this as okay, 2 to the power 4 and 3 becomes 2 to the power 7. 7, you can eliminate 7 from the 2 to the power 16, gives you 2 to the power 9 cache lines. Okay, so 512 cache lines are there after this calculation. But because it is a set associative cache, we need to divide these cache lines into the number of sets. So the number of sets should be equals to the number of cache lines divided by the p way. P way here is 16. So 2 to the power 9 divided by 16, which is 2 to the power 4, gives you 2 to the power 5 sets. Okay, so hence there are 32 sets. Fine. So once you have the number of sets, okay. So once you have the number of sets, the set field is going to be 5 bits long. Set field is going to be 5 bits long because 32 sets are there. That means log of 32 add base 2 gives you 5 bits. Word is depending on the block size. Okay, which is actually 4 bytes, sorry, 4 bits. Okay, and the remaining are the tag bits. So 9 going makes tag bits as 31. Okay, let me correct this thing. Word is actually 16 words. We need to convert this word in number of bytes. So this is going to be 16 into 2 to the power 3 bytes. So this is going to be 2 to the power 4 into 2 to the power 3 bytes. Hence, the number of bits required are 7 bits, not 4, because the block size is given in words. Okay, so let me correct the tag bits also. So if we have 5 bits of set and 7 bits of word offset, so this will make 12. So out of 12, 40. Out of 40, if 12 is gone, the remaining is 28 bits for the tag memory. Okay, so 28 plus 12 is going to be 40. Fine, this is now okay. So moving on, we need to find the tag memory size. Now, what is the tag memory size? Tag memory size is equals to the number of sets multiplied by the p way, which is 16 in our case, multiplied by the number of tag bits, the number of tag bits in each set or per set. Okay, so number of sets we are having 2 to the power 5. P way, which is 16, we can write it as 2 to the power 4, multiply by number of tag bits. Okay, number of tag bits we are having 28 bits. Okay, so after multiplying 28 and 512 will give you the number of total bits in the tag. Okay, that should be your answer. So remember, in this type of questions, the unit plays the important role. Unit plays the important role. So make sure the unit of all the values must be same. So some of the values have the unit as bytes, and some of these values are having the unit as word. So you need to convert them otherwise in the words or all in the bytes form. Okay, so it's better to convert the higher unit into the lower one. So let's have the similar units and before get into the calculation. So the answer should be 14336 bits as a tag memory size. So if one tag is of 28 bits, the number of sets are having number of occupancy in the tag bits. We need to find that tag memory size. Okay, so how many number of bits are going to be occupied or used by the tag is going to be the tag memory size. Okay, this is the answer of the given question. Okay, let's have a look, then we can move to the next one. In architecture, the only thing you need to get working on is the calculation. All you need to do is the calculation, because there are so many questions that comes in the numerical basis. So only if you if you need to find the accurate answer, you must have the thorough knowledge and formulas or equation, and the calculation is very much important. So CS guys, especially because we don't have so many subjects based on the calculation or numerical based question, COA might get bit tricky. So keep practicing in the virtual calculator once you go for the examination. Okay, so keep practicing the virtual calculator. This will help you, or this will save your time, precious time during the examination. Fine. Let's move on to the next one. Let me shift this question somewhere else. Okay, fine. Fine. This is our second last question. Then we are going to have some doubt clearing session. Suppose we want to read 4096 bytes in the programmed IO mode of transfer. This is IO structure question. Suppose we need to read 4096 bytes in programmed IO mode of transfer. The bus width is 32 bits. Each time an interrupt occurs, it takes 4 microseconds to service it. Okay, so the bus width is 32 bit. That means all you need to transfer is 32 bit at a time. But to transfer this 32 bit, it will take 4 microseconds to service. Okay, then how much CPU time is required to read all of these bytes 4096? So this is very easy question. All you need to do is find the number of time taken to transfer one byte. So one byte time taken is going to multiply by 4096 will give you the number of time, sorry, the total time taken by the CPU to transfer or read 4096 bytes. Okay. So first thing first, transfer 4 bytes, which is actually given as in 32 bits, takes 4 microseconds. Okay. That means how much time one byte will take? 1 microseconds. If 4 bytes is going to take 4 microseconds, 1 byte is going to take 1 microsecond. That means how much time 4096 bytes is going to take? 4096 microseconds. This is very easy question. As the options are given in milliseconds. Okay, let me correct this one. This should also be in milliseconds. Fine. Okay, so based on the unit of given options, we should convert this microseconds into the mini. So this is going to be 4.096 milliseconds. So milli is 10 to the power minus 3, and this is actually 10 to the power minus 6. So based on that, the answer should be 4.096 milliseconds. So answer should be option A. Fine. So all we did is 4096 bytes transfer time we need to calculate, and bus width as given is 32 bits. Each time when they transfer 32 bits of size, it took 4 microseconds to service it. So if 4 byte takes 4 microseconds, that means 1 byte will take 1 microseconds. Then 4096 bytes will take 4096 microseconds. Okay, converted it to the given options. According to the given options in milliseconds will give you 4.096 milliseconds as the right answer. Okay. So let's move on to the last question of this session. Find the following binary number as an IEEE single precision float. And the binary number is already given 0.1010 and continued. That is, bits 1 and 0 are repeating infinitely many times to the right of the binary point. Okay. After the period sign, 1 and 0 are actually repeating for the infinite number of times. All we need to find is the IEEE single precision float representation of this given binary number. But in that case, we should have the format as 1 point and mantissa. The format should be look like this only. So to convert this, what we actually going to do with this question is, let me write down the steps here. So the value 0.101010 and continued can be written as 1.010101 up to multiply by 2 to the power of minus 1, right? We can write this particular binary value, in this format also. So same value can be written in many formats. So we can write this in here so that we can have the uh, particular format representation. Okay, all the values must be there, because for single precision we already had the formula of minus 1 to the power sine multiplied by 1 point m, which is mantissa, into 2 to the power biased exponent minus 127. So we need that format to be solved. Okay, so for that we actually shifted one period sign so that we are having 2 to the power minus 1. Okay, as the sign bit is 0 because the value is going to be positive, so the sign bit is 0 and the exponent, which is the biased exponent, is 126, because the format was this: minus 1 to the power s into 1 point m into 2 to the power biased exponent minus 127. So if the 2 to the power is minus 1, so how much is the value of biased exponent? This is actually 126. So that 126 minus 127 will give you the actual exponent minus 1. Okay, fine. So biased exponent, we already written this equation in the above question somewhere. Exponent is equals to actual exponent plus the bias. So this will give you actual exponent, which is minus 1, plus the bias, which is 127, will give you 126. So 126 is going to be the biased exponent. Fine. About the mantissa. Okay, and sorry, to represent this biased exponent in 126 as a binary, what should be the binary of 126? So 126 binary, I think it should be except 1. So 1, 1, 2, 4, 8, 16, then 32, and then 64, and 128 should be 0. I think this should be the binary of 126. Okay, we need to write it in the given format, so that we need to find the binary of 126. Okay, so this is going to be 64 plus 32, which is 96, plus 16 is 112, plus 8 is 120, plus 4 plus 2 is 126. Okay, so this is going to be the binary of 126. We need it in the future. Okay, hence the 32-bit single precision floating point representation will look like. So let's have this representation over here. One bit is reserved for sign, 8 bits are reserved for biased exponent, and the remaining is for the significant or the mantissa. So sign here is 0 because the value is positive. This is 1 bit. Okay. Biased exponent, which is 126. We already have the binary of 126. 1, 2, 3, 4, 5, 6, and 0. So we'll have 8-bit representation of biased exponent. And the mantissa, we have already calculated it as this. This will be our mantissa. So mantissa will be 0, 1, 0, 1, 0, 1, and continued infinite times for 23 bits of length. Correct. So based on these, the hexadecimal format should be the first 4 bit is actually 0011, which is the value 3. Then 1111 is actually the hexadecimal value f. Then 0010, this is actually the hexadecimal value 2. And then 1010, which is actually 10. 1010, which is actually 10. That means a. And this 1010 is going to be continued till the end of 23 bits. So every time the 4 more values we will have as a, a, and a, which makes it 8 byte, or sorry, 8 nibbles of representation, which is 32 bits. So this 32 bits representation in hexadecimal is going to be 3f2 and 5 times a. The correct answer is B. Okay. So either way, you actually need to represent this particular floating point question or every floating point value in either this format or in the hexadecimal format by using this representation of sign, biased exponent, and the mantissa, which is actually 32-bit representation. Okay, so this is about single precision floating point IEEE values. Okay. So now if you have any doubts regarding all any of the question, just let me know, or any concept you need to find out. Okay, this is all about the COA tutorial questions. Just let me know. We can end this session also if you don't have any doubts. But if you have any doubts regarding any of these questions, just ask. But before that, all you need is the uh, detailed or conceptual knowledge of the concepts, and the depth of that knowledge of the concepts, and you must know all the formulas and equation behind this. So before going for the question solving, just have the revision of the whole subject once, because there is so many things to remember and so many formulas and equations to remember, especially in architecture. Okay. So organization architecture is very important thing, because in 2020 year it already covers 11 marks of weightage, which is usually higher than the previous years. Okay, in the past years the weightage of architecture and organization was only 5 to 8 marks, and now so in question number 5, the word offset is not 4 bits. Okay, let me have the question first. Okay, so actually the word offset, the word offset is actually depending on the block size, whatever the block size is. Okay, block size is already given. The block size, cache block size is already given, which is actually 16 words. But we have all the other figures or values in the form of or in the unit of bytes. Okay, so we need to convert this word into bytes as well, and there is a given thing that one word in the main memory, sorry, data words are actually 64 bits. So 64 bit is going to be one word length. So one word is going to be 64 bits long, which is actually 8 bytes. So we have the block size of 16 into 8 bytes long. So this we already mentioned here, that 16 word of block size, which is actually 16 into 2 to the power 3 bytes. Okay, because we are going to convert everything in this particular form. Okay, so 2 to the power 4 and 2 to the power 3, which is actually 2 to the power 7 bytes. So make finding the log of 2 to the power 7 n base 2 will give you the 7 bits. Okay, so that is why we need to convert. So always remember what unit the question is asking for. Okay, so everything is already in bits, and bits is going to be converted from bytes. So first you need to convert word into bytes, then into the bits. Okay, because word length may vary, because yesterday we just took the example that word size is depending on the word length of the processor. If the processor is changing, the word length is also changing. Okay, so all we need to convert the words into bytes and then into the bits. Okay, yeah, correct. Any other doubt regarding any other question? I'll rather suggest you once go with this PDF. When you have this PDF after the session, before going with this, just have the just you must have the revision, just to take the revision of the topics we just covered in the questions, so that you can have better understanding and explanation. Okay, so this is not the way that set associative cache or something like the cache memory is again very vast topic inside. Okay, so we have so many things in the cache memory also, just like the main memory also. Or main memory configuration is again the very important topic. We already covered the cache memory and main memory thing, but main memory comes with different concepts also. So what is the main memory chip configuration, what how the main memory is going to get configured, why the configuration is actually required between these memories. This is all we need to find out before get into the questions. Always remember, concepts are behind the questions. You must have the thorough knowledge of the concepts before get into the questions. So when you go for the questions related to cache memory or main memory, just have everything you need to find about the cache memory or main memory first. Learn that thing first before getting into the questions. Okay. So the configuration is required because uh, the architecture or the hierarchical design we just mentioned here, CPU, cache memory, main memory, and secondary memory. CPU is again the electronic device. Cache memory is again the semiconductor based. This is actually main memory is chip based. Okay, secondary memory is magnetic disk. So because the manufacturing of all the devices or all the peripherals is different, their transfer rate is different, their component is different, their quality is different, their read and write thing is different, their size is different, their speed is different. Because there is a difference in so many things factors, we actually need to configure them according to the CPU, which is the master of the system. So whatever the CPU needs, we need to convert accordingly. Okay, so based on the CPU, we actually convert the or we actually configure the main memory first. Once the main memory is configured, we configure cache memory based on the main memory, because eventually you need to transfer the main memory block to the CPU. But to transfer that, we need some intermediate memory between between CPU and the main memory. So whatever the main memory block is going to be the CPU, you must have the same representation of cache memory as the main memory is having. So whatever the main memories look like, you must have the cache memory representation as well. So based on the main memory, the cache memory is going to be configured. But before that, main memory is going to get configured based on the CPU's requirement, because CPU is the master. So this is how the memory organization is taking place. Okay, so the thing is, everything is wanted by the CPU. So CPU will tell you what data he actually wants to process or write or anything. So CPU will send the request. CPU will generate the request. That request comes like this. There will be some type of operation, or type of operation. In place of type of operation, you can say signals, along with some address field. This address field is based on the main memory addressing. Okay, and the control signal is the type of operation like read or write. Okay, because all the whole main memory is basically the collection of cells. The whole memory basically is the collection of cells. So each cell is working like the rooms we have in the real life environment. So every room has some doors. That door we can use for going inside and outside. Similarly, each cell only remember two signals, only recognize two signals. One is reading the cell or reading the data from that cell, or writing that cell. So CPU generate the request which actually eventually looks like this one, along with control signal, what operation he actually wants to do, along with the address field. This address field is for the main memory addressing. So based on this length of address field, first the main memory is going to get configured. That is what we learn in memory chip configuration. So memory chip configuration, or memory, is going to configure based on the CPU generated request. This is the CPU generated request. Okay, so based on the CPU request, memory is going to configure. Now, if the memory is configured, memory is going to transfer some memory block to the CPU, but it cannot do it directly. It has to do it by using some cache memory in between. So suppose the main memory block is of this much size, suppose 2 bytes. So we can't have cache memory uh, separately with some another block size. We should have the cache memory block size is similar to this one, so that we can have the main memory block inside the cache memory block. So the representation, the size may vary between cache memory and main memory, because cache memory is again very low size component. Okay, so cache memory is could be a low size component, but the representation or the structure of cache memory should look like the main memory, so that we can have the main memory block exactly in the same way in the cache memory. Once it have in the cache memory, it can be read or write by the CPU. So everything starts from the CPU, because CPU is the master of the system. So whatever CPU tells you, the things are going to get configured again and again. Similar thing is also going with the IOs. IO are also the slave in the uh, organization or architecture. Okay, so whatever CPU is going to tell, IOs are also going to get configured. So this is the concept behind everything in the architecture and organization. So CPU, all you need to look about the CPU, what actually CPU wants, how the CPU is going to operate, what are the instruction cycles CPU actually follow, and how the interrupts are going to use by the CPU. If you have this thorough knowledge about this, it will help you to learn each and every topics of the architecture and organization. Fine. So let's go with try to go with that particular thing. Just I just told you now, and then you can go with the full revision of the subject. and the question afterwards. Fine. First, know the basics of of the subject. It will help you a lot. Okay. So if you have any further doubts, let's have them, or and we can end the session today. Any doubts? So let's go with the uh, streaming once, and you will have the PDF afterwards after the session, and maybe then you must have some doubts. We can clear it if you have any doubts regarding this particular session or the previous session. So you can have this information or knowledge to the TGA team. TGA team will help you out with this, and they can manage the doubt session also. Okay. So let's end the session today, and you may have some doubt session in the uh, you can have the doubt session later on by coordinating with the TGA team. Okay, let's end this session now. Okay, thank you guys.